Hello guys, let's talk about OPAMP layout guidelines for beginners. Okay, so all the while we've been seeing that wherever we go for analog layouts, the basic uh, circuit what we use majoritarily is your OPAMPs itself, and OPAMP has got a bunch of critical circuits which are used internally. So obviously, whenever we are doing OPAMP over here, it has to be done with certain precision, and it's one of the very simple layouts, simple modules, what we generally, basic building block, what we can call, okay, of analog layout design. Okay, so and you know that op-amps are used in as comparators, amplifiers, sample and hold circuits, or lots of other applications, mathematical applications and all of that. So majoritarily, if you see lots of analog circuit is a bunch of current mirrors and differential pairs, and that's what we see inside an op-amp as well. Okay, so let's see what all we are going to learn in this session of layout guidelines for OPAMP. Okay, so first of all, the most important thing here is it's not about just making the connection, connecting sources and drains and getting the design LVS clean. You also need to know where to tap it. Okay, where to make a proper connection when you are connecting a device and when you're connecting a guard ring, all those things. Let's have a brief idea about it. Okay, where exactly one needs to make certain connections when you're connecting the layouts. Okay, and then let's jump into how to do the layout of a op-amp. Okay, so what's involved in that? Okay, and then another important thing here is we know that op-amp consists of a current mirror, a differential pair, and a biasing transistor. Okay, so let's take current mirror and see what is the matching technique we can apply. What are the things? I'll be taking some screenshots and trying to show you how to make the connections. What is the importance of each and every connection? Okay, and then again, how to connect the dummies and what's the importance of connecting the dummies, and then how to make a connection correctly. We know that in our current mirror, the we have a diode connection connected device. It's got a gate and drain connected, but there's a specific way to make a connection when you're doing the layout. Let's look into that as well. And then obviously how to match a differential player, and then I'll be giving you a complete floor plan of a op-amp, how to place the devices, how to share the guard rings and all of that, and then finally how to make symmetrical routing connections. Okay, and finally a little bit about power connections for the op-amp. Okay, so let's take one by one here. Okay, so if you see here, this purple thing might be a little dark to understand. Let me take another color here. Let me take orange. Yeah, there you go. If you see here, just take a simple example. I'm just trying to talk about how to make a connection. Okay, you've got a PMOS over here with a gate connection, source and drain. This is your AVDD over here, and you've got a guard ring, okay, a N-well guard ring. Even that has got the AVDD connectivity. I have given it purposefully over here, okay. And now you see that there is a M4 power supply over here. So now, if at all you have to make a connection from a device to the power supply, how would you do it? Okay. Majority of the guys, majority of the learners or beginners or even the experienced professionals make a mistake of connecting the source to the guard ring itself, which is not right. Okay. They say that, yeah, obviously even the guard ring has got the AVDD connection. Why not pull the power supply from the guard ring itself? But keep in mind that your guard ring is not to provide the power supply for the device. It is used to collect the minority carriers. Okay, that's the reason for a P plus you've got N plus guard ring, the opposite one. It provides a low resistance part to the substrate to take care of a latch up effect. Okay, it is not to provide power supply to the source of your device. Okay, so moving on. Okay, people make this mistake over here. That's what I'm trying to show. Okay, so here, this is the device AVDD. People make a mistake by connecting it over here. Yeah, this is just a single transistor. So just to show how to make the connection, I have written this is your V out and this is some gate connection here. And again, the guard ring is tapped to the power supply net over here. Okay. So as I mentioned, guard ring is to absorb the minority carriers and not to make a power supply connection. Okay. So the correct way to make a connection is, right? So this is a device here. My power supply is in M4. So what I got to do here is I need to pull up my M3. I'll take M3 over here, pull it up and directly tap the power supply from the top power supply line. I'm not going to tap over here. There is no connection over here. I'm not going to take any power supply connection from the guard ring. This is not meant to be connected here. Your source needs to be directly connected to the power supply. And you need to connect the guard ring separately. So you'll be dropping either you place it over here or here. Just for visibility purposes, I have placed the power supply over here. Ideally, you can, in the lower technologies, you can very well place the power supply net over the device itself. Okay. Here, just for explanation purpose, I have put it over here. Okay. So keep in mind that whenever you are connecting a device, be it a current mirror or any transistor, PMOS, NMOS, whatever it is. Okay, your power supply to the device should come directly from the power net and not from the guard ring. And you need to tap the guard ring separately over here. The purpose is very different. Okay, so do not make the mistake of making incorrect connections. So that's one of the basic and important thing which I wanted to put it across before I get on to the layout aspects of what is a OPAMP. Okay, so now OPAMP over here, as you can see, as I mentioned, this is a current mirror. So generally, the circuit designers, they tend to put these boxes like this and give an indication to the layout guy that these are the transistors which needs to be matched. So we know that this is a current mirror configuration, which means what? There is gates are connected and you've got a diode connected device over here. Now assume that if at all you had another leg over here, okay, and for example you've got this net connecting over here, just for example there would be n number of such legs, if at all they are larger op-amp or larger current mirror bank. So in that case the easier way to figure out is just click on this and highlight this net. Okay, highlight this particular net over here. It would highlight all the nets to which this gate is connected. Thereby, you will be able to figure out what are all the mirroring devices which come under the category of one single current mirror, or should I say, which are a part of a single current mirror. This is the diode connected device. This will be your mirroring devices. An easy way of figuring out. Generally, circuit designers will be there in their mood and they would end up making connections for their ease to understand. But if it's an experienced layout person, yes, they'll be able to figure out. But for the beginners, that's the easiest way to figure it out. Okay. Now, another one over here is a differential pair, wherein it's highlighted that this also needs to be matched. Okay, so let's take one by one and see how this can be done. Okay, so I have, for the sake of simplicity, I have taken two transistors A and B. These are two, and this is two. I will go with a interdigitization related concept because it's a single dimension. Okay, we are trying to cancel the gradients in one direction. So I will place the diode connected device in the center. That's the rule of thumb when it comes to matching a current mirror perfectly. Bottom line, just keep the diode connected device in the center. Then you've got the mirroring devices over here, and in the end, you'll be placing the dummies. And just a picture over here, just to highlight and show that this is how it's done. Okay, and obviously you have to place the guarding around it. Okay, that's how you do the floor plan, or that's how you match a current mirror. Here I have used only two devices, because it's a simple op-amp. As we go further, you might come across much more larger current mirrors, then the numbering will be different. Okay, just to show you an actual picture in the layout. So this is how it's done. So I have taken here two devices here, as I said, 2A and 2B, and one dummy. Okay, there are two dummies, one on the right, one on the left. So keep in mind that whenever you're doing the floor plan or doing the matching of sensitive devices, considering current mirrors or differential pairs, keep all the devices in the center. In this guard ring, you see that all the devices are in the center. These are my functional four devices. This is A and this is B. I have done the matching over here, and these are my dummies. I have shared all the sources and drains, and I have added a guard ring around it. Note that you need to keep the guard ring as close as possible. Don't give too much of room over here. Now, by placing the devices in the center, you're taking care of well proximity effect. Okay, so the devices in the center, okay, will not experience that variation in the VT because of WPE effect. That's one of the reasons we tend to keep the transistors in the center. Okay, so the ones at the boundary will experience a bit of variation because of doping effect of the well. Okay, you can study about what is WPE effect to get more insight into that. But in short, when you're doing the layout, always keep the devices in the center. Now you may ask me, why am I using dummies? So as a part of the stress effect, there to deal. So whenever the etching is happening over here or something of that sort, right? So you need to take care of the stress effect on actual functional devices. Okay, so the stress effect, like, okay, simple. If I have to put it across this way, let me just give a quick explanation here. This is a device here, again another device here. Sorry about the picture. So this guy over here and this guy here, these are the two devices. Okay, this will add stress to the diffusion regions. The STI, the shallow trench isolation, will add stress to the devices, which will impact the mobility of the charge carriers, which will impact the transconductance, which will impact again the threshold voltage of the devices. All in all, there's a kind of chain link connection over there. So in short, to deal with the stress effects, we end up putting dummies. Okay, that's how you place the functional transistors over here, and then two dummies and a guard ring. And again, keep in mind, when you're making a connection over here, do not pull the source connection from the guard ring. It's a strict no-no. Use a power supply strip over the device itself. Connect it directly. Let the guard ring be connected separately. Let the source be connected separately. Okay, and some settings would be done in the from the CAD guys to filter off the dummies. When you're running LVS, it wouldn't cry. Else, you may have to add two dummies over here. Okay, because you're using one on either sides. For lower technologies, I mean the higher nodes, yes, it's okay to have on either sides. But as you go to the FinFETs and all, it's expected to have dummies all around. Okay. So now another important thing here, when you're making a connection with a current mirror over here, right? Okay, we know that. Let me just draw this quickly here. This is your basic current mirror over here. I mean, the picture is reversed over here. One thing to note over here is whenever you're making a gate connection over here, do not connect this to this particular net. This is assume that this is a wire. Okay, this is a wire which is connecting to this gate connected device over here. This is the connection which is depicting over here. Whenever you're making a connection to the layout, we know that these are connected. We know that the gate and drain are connected over here. But do not pull out the drain connection from the gate itself. We are not pulling out the correct one. We need this guy here. We need this guy. Okay, so if you're connecting over here, the voltage at this node and this node will be different when you're making a connection over here. So it becomes very important. You make a connection. Yes, gate and drain are connected, but when you're pulling out the current, pull it out from the drain connection, not from the gate. Just because gate and drain are connected for this leg, no, don't pull it out from there. Okay, so it's very important you make a whenever you're pulling out the connection, pull it out from the device, the drain connection. Okay, so now moving on to this guy here. Now matching a differential pair. Okay, we know that differential pair, yes, the default is the common centroid technique, which we are trying to implement over here. We have taken 4A's and 4B's here. Okay, so how do we implement that? So I have added 2A's over here, 2A's over here, B's and 2B's in 2 rows, and I've added 4 dummies here. Same thing in the layout, I have shown it this way. Okay, so here 2 devices, 2A's and 2B's, again 2A's and 2B's. Note that I have shared all the devices. I've added the guard ring, my device is in the center. In this picture, I haven't shown the dummies. So probably in the next picture, yes, you will be seeing the dummies as well. Okay, same thing, same concept. Now, all in all, if I have to give you the overall floor plan of an OPAMP, it would look something like this. This is the current mirror, which we spoke in detail. Okay, so now you've got all the devices well as connected with the 2 dummies over here. This is this, this is this. Okay, now I have added this guard ring over here. This is the differential pair, 1, 2, and this is the dummies. If you can see, this is a dummy here, this is a dummy here, 4 dummies. Okay, and now I have tried to share the guard ring because even these two, this is also NMOS and this is also NMOS. These both are NMOSs. Generally make a practice that whenever you're having matching certain devices, do not add other transistors into the same guard ring. Okay, let that be separate. Okay, so that's why this biasing transistor is placed separately in a separate guard ring, even though it's the same transistor. You got to just make a practice of that when you're doing. And obviously, this is just a transistor over here. We are not doing any much of matching over here, so we can just keep it that way. Okay, we are not using dummies over here for biasing transistor. Okay, so this is the overall floor plan, neat and straight. So one thing you need to keep in mind is whenever you're doing a floor plan, keep the transistors in such a way that you would be able to draw straight connections. The routings should be symmetrical. Okay, let's see how that is done. Okay, so let's take your current mirror again. With the layout, I'm just trying to show you. This is your device. Okay, this is your device with the dummies. These two are dummies here. Okay, this is the gate and drain connection. I'm pulling out directly over here. I have drawn the power supply over the device. Okay, just for the sake of explanation, I had shown it on the top. But here, if you observe, I have drawn the power supply net, that is M4, on the device itself. It is allowed in lower technologies. Even in FinFETs, it's okay to do that. Okay, so if you observe here, the way I am tapping is different. I'm tapping the guard ring directly to the power supply net here and here, right? The source AVDD is being directly tapped to this net. I'm not going through the guard ring. I'm tapping it directly to the power supply net. Okay, so that's how you got to make a connection for current mirror. Same thing, I would say when it comes to differential pair, the routing has to be very, very symmetrical. So what I would do is, if at all I have to make a gate, because these two devices are over here and these two devices are over here. Same thing, A, and B, B. Okay. So how do I make a gate connection? So I would space them apart a little bit, then draw a zigzag connection like this. Right. And then overlap this and go. So my V1 and V2 will be taken on left side. These are my connections, dummies. Yes, since these are dummies, just for the sake of explanation, I have connected them over here. But ideally, since it's a dummy, it is okay to be connected. But if it's a functional device, it's a strict no-no to connect to the guard ring. Okay. And now, if I highlight these nets, you can see that these are the gate connections. Okay, the inputs V1 and V2 over here. These are the source and drain connections, whatever, the for both the transistors. If you see here, you can see a proper symmetrical routing. One very important thing here when it comes to differential pair is the routing has to be symmetrical. Okay, that plays a very important role for the functioning of your differential amplifier. Now, finally, all in all, if I have to say, this is the layout of the structure of the op-amp over here. This is the power supply net which is running on the device over here, here on the biasing circuit. Now, if you see here, the lines are running down straight. And this is the same thing which I've highlighted and shown you in the picture over there. So ensure your routings are symmetrical and ensure that the lines are running straight from top to bottom. Okay, and the power supply strip is on the device. Okay, so that you don't add extra resistance or whatever whenever you're connecting to the device. All in all, the layout looks like this. I mean, okay, so that's all about your making connections to the op-amp. Okay. Now, if at all I have to say, that's the brief thing what I mentioned about op-amps over here. Now we've got another new course which is updated on the Semionics-academy platform, wherein we've spoken detailed about analog layout matching concepts. So if you see here a proper analog layout, these are obviously the pictures from the internet. Uh, you know, so here this is just to show you that how matching is done. So we have discussed in detail about lots of matching concepts from the basics till the advanced, taking lots of uh, practical real-time examples and scenarios, how to match the devices, how to match the resistors, capacitors, BJTs, matching routing lengths. All of this stuff is explained in detail. So for the beginners and for people or the fresh layout engineers or people who want to switch from digital to analog domain, the standard style guys or custom digital guys, I think that would be a good starting point. So you can take advantage by enrolling into this course of analog layout matching techniques. Okay. Hope this helps. Thank you. That's semionics for you.